next year. All right. Lesson 3 for work and energy. Let's get to page 10, as I said. A lot of this you would have covered in year 10, all right? Conservation of energy. The key thing here is putting the first equation down, the logic to get that first mark. This is going to help us solve for our unknown. There's always an unknown. Determine the mass, determine the speed, determine the height, determine how much was lost, something like that. You can get that by setting up the question, all right? So, this is another law. We looked at conservation of momentum. That's a law that is always conserved. Same goes for energy, okay? So, the total energy in a system is always a constant value, and you can write that a few different ways. You could say the sum of energy initial will equal the sum of energy final. We can expand out what the sum of the energy is, all right? The total energy, let me try and write that a little bit neater, can exist in the 3 forms that we are currently aware of. That is kinetic energy, potential energy, and then we're going to add thermal energy. Well, I'm going to write it as E lowercase t. So don't confuse it with capital T. All right, different teachers, different textbooks will have different subscripts. Some might say ET, some might say sigma, which is the sum of, okay? If you have initial, you'd have to have an extra subscript. For example, the sum of energy initial is going to be the sum of kinetic initial plus the sum of potential initial plus the sum of thermal initial. So it's getting tricky now. We're going to have 2 different potentials, one at the start, one at the end. And so you now need to have 2 subscripts. Yes?
In terms of like thermal energy, isn't that the same as kinetic energy?
No, not at all. I'm going to show you in a moment. Thermal energy is the kinetic energy of all the particles, but it's the disordered kinetic energy. So let's just get to, I've placed these first 2 in a bracket. These ones are considered mechanical energy. And we normally consider mechanical energy high grade. All right? Now, I do write this in my year 10 booklets, Brady. And so if you had me in year 10, this might be familiar, but it's called high grade because it is very easy to convert between or transform. Easy is the key word here. Easy to convert between, and you have a very high efficiency. Yes, Cameron?
Does that mean it's easy to go from one mechanical energy to another, but not a mechanical energy, whatever the other thing is?
Well, here's my example. I'm going to use this Yum box. Right? Now, I'm going to throw this box up and I'm going to catch it. Ready? And go. When it was in the air, it was converting between kinetic to potential and then back to kinetic. All right? Now, I'm not going to do this with the Yum box. I'm going to do this with the whiteboard marker. Right? Now, I'm going to talk about the final one. Thermal energy is low grade because it's very difficult to convert back. Ready? Watch this wonderful transformation. You don't have to see it, but you know what's going to happen. Ready? Here we go. Kinetic, potential, kinetic, bang. Where's all the energy gone? Sound, heat. If we filmed this with a thermal camera, when it smacks into the table, you'd see this big hot spot. That's what the SNCO, the hot spot in cricket. They look for that little thermal part where heat has been produced. Now, we say that all of the energy is still there, it's just been transferred or transformed, okay? So it didn't just disappear, it was converted to sound and to heat. And that energy has now gone from mechanical to heat. It's gone. I can't collect that energy back. I can't say, let's get all the sound back, let's get all the heat back, and sort of reverse entropy, boop, there it goes. All right, we can't do that. All right, once it's converted to heat, very difficult to get back. Now, I would say for that scenario, impossible. We could not get all of the sound back from where the molecules in the wall and the air and your face now have absorbed some of that energy. Can't get it back. All right, so let's just add to our diagram here heat, which we already remember from the first topic, thermodynamics, is low grade energy, and it is difficult to convert back. Okay. As I said, not impossible, but difficult. The example that I give every year is, oh, that's a very bad oblique drawing, is a sort of steam engine. If we took a whole lot of coal and we set fire to it and we sort of located it in a furnace, all right, we would be releasing all of that chemical potential, high grade. We would be creating a whole lot of heat. We'd probably have some reservoir of water. Where's my water? There it is. A whole reservoir of water, which is going to turn into steam, and then maybe that steam could turn some kind of piston that's sitting in a cylinder, and so we can get, this up and down motion. We've now taken some heat and converted it back to mechanical energy. But this process, very inefficient, all right? You're losing a lot of heat. And so we might only have, around about 10% of the energy in a steam engine actually go from the coal to the piston going up and down, okay? So your old steam engines, your trains, combustion engines in cars, we still do this. We convert heat into mechanical energy. The standard number that we throw out for, this is probably back when I was a student, your petrol engines of your 1998 Nissan Pulsar is 25% efficient. So only 25% of the chemical energy actually goes into making the car go. All right? The 75% is made into heat. It heats up the engine block. It heats up the oil and the coolant that's running through the engine. Right? The exhaust coming out the end. The air traveling in through the radiator then passes out hot underneath the car. All right? So nowadays, our cars are probably slightly more efficient, and now we're looking at electric cars, trying to get a higher efficiency. We don't want to waste the energy. Yes?
I was just going to say Formula One engines are 55%.
55%. Is it? Oh, there you go. So even your Formula One engines, 55%, you're losing 45% to heat. And they try and reclaim some of that energy with the KERS system. When the Formula One cars brake, generally when a car brakes, it just makes a ton of heat, all right? You have a brake pad that's going to grab against the rotating brake disc, and all that kinetic energy of movement goes into heat. Gets very, very hot. What they try and do with the KERS, the kinetic energy reclaiming system, I think, they take some of that heat and it converts it into like a battery. It stores that thermal energy, converts it to electrical potential. And they say when they're using the KERS system in Formula One, you can get a boost of 100 horsepower for about 3 seconds or something. Yeah. Do they still do KERS in?
I think it's
Kinetic energy recovery system.
Recovery.
They use an MGUK now.
Say what?
An MGUK is what it's called now.
MGUK.
Yeah.
All right, different acronym, but same thing. Yeah. All right. So, with that in mind, let us consider this. This is still work, but we're going to just make sure that everything is accounted for. What this conservation of energy law is just making sure the books are balanced. What we have at the start must be present at the end, but it might be in different forms, okay? So, let's just start with a 10 kilo mass, so 10 kg. Let's add some stuff here. Let's assign a convention at the top that forwards is positive, backwards is negative. We apply a force. Oops, that's a bit too much. Let me go down a little bit. We apply a force forward of plus 100. And while that acts, there is a backwards force of friction, negative 30. Okay? And then we apply that over a distance, very poorly drawn there, of 5 meters. All right? Now, we have this concept of work. The work done on the crate. Well, here's a little trick here, gentlemen. The work that's done on the crate is the net force. The crate only receives the net force. So we're going to take the net force, so work done, transfer of energy equals E final minus E initial equals net force times S. Could somebody tell me what the net force is?
70 newtons.
Plus 70, 70 to the right. Normally we would work that out, but we're running out of room and time, so we'll go plus 70 multiplied by 5. It gets 350 joules of mechanical energy. Now, look at our diagram. The cart is not going up into the air, it's not going down into the ground, so it's not gaining or losing potential. So we could say that your final energy is going to be a half mv squared plus a half mgh. But there is no mgh. So that's all going into kinetic energy. So we could say, take that down to here and go work done equals a half mv squared, as I said, plus mgh final. We can cancel that out. So we've now got 350 equals a half mv squared. Let's throw the values in. A half of 10 is 5. V squared equals, whichever way you want to do it, let's just solve for v. V equals the square root of 350 over a half of 10 gives us 8.36. All right, that's how fast the cart is traveling, because it has 350 joules. But there was a work done on friction. Now, it's a bit weird how you word it, work done by heat, work done by friction. Friction has acted over 5 meters. So imagine take your hand and you slide it across the table. Friction is acting over that distance to make heat. So the next work done, we'll say work done equals, delta E equals FF times S equals negative 30 multiplied by 5 equals negative 150 joule. In fact, let's just get rid of the negative for now. Sorry, let's just change it back to positives because I want to just show you. We've got 2 forms of energy now, right? So work was done by a person. We haven't considered that person yet. Oh, the person should be over the other side. The work done by the person has gone into 2 forms. Some of his work went to kinetic energy of the cart, and some of his work went into heat. And we've got those 2 numbers here. He put 350 to the cart, he gave 150 to heat, so the total work that he did, 500 joules. That's a formatting error there, apologies. Scribble out the person, it should be up here, person. Okay. Well, this is going to be the work done equals the applied force times S. So he applied 100 newtons over 5 meters. So he did 500 joules. So what I just wanted to show you is it is conserved. All right? If that person transferred 500 joules out of his body, it has gone somewhere else. It hasn't just disappeared. Okay? The gentleman might be a bit confused. After 5 meters, he only observes that the 500 joules has only resulted in 350 joules of useful energy. There seems to be an inefficiency. There seems to be energy missing. But it's there. Remember, we're going to draw in the red wafty highlighter heat. More colours, waftiness of heat. The heat is there. All right? All of that friction has heated up the surface of the mass, the surface of the floor, and all those particles are now jiggling. They're still jiggling with kinetic energy, but it's erratic, chaotic, disordered energy. All of the particles are jiggling around in various motion, right? Whereas the cart, they're all traveling in the same motion. They're ordered. So that's one other way to look at mechanical energy. It's ordered energy. If you have a ball traveling along, you've got ordered mechanical energy. If you took that ball, put it in the oven for half an hour and bring it out, ooh, hot, 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 and then you throw it, you've got heat as well as kinetic energy, all right? But it's only the kinetic energy that is useful, all right? So you can start adding them all. Oh, and by the way, that ball was above the ground, wasn't it? So not only you've got the moving energy, you've got the disordered heat, And you've also got these particles above the ground. They could fall to the ground and convert that potential energy to kinetic energy. So it's a very philosophical way of looking at work and the potential to transfer energy between one form to another. Yes, Cam?
So effectively, heat is the scalar version of velocity.
Heat is the scalar version of... No, I don't know what that means. Heat is just the disordered kinetic energy of the particles.
Yes, sir.
It's a...
But the average velocity of that would be almost zero, right?
The average velocity of all that... Yeah.
Yeah.
The sum of the average velocity of the particles is zero, but they're all jiggling phenomenally fast.
So
Now-
effectively, heat is to velocity as distance is to displacement.
Yes, I'll pay that, yes. Last question, gents. We figured out that this thing was traveling 8.36. Let's suppose that he lets go. All right? So let's just bring down a new scenario. We now have the mass traveling at 8.36, and it still slides along. If he lets go, there's no more applied force. There's now just a backwards force of friction, which still equals your negative 30. All right? So now we could go, all right, how far would this cart slide? Again, we could do SUVAT. We could do find the acceleration, do v squared take u squared over 2as, but no, we're in work and energy mode. We want to do that work is the transfer of energy, which is E final minus E initial, which is equal to F times S. Okay? Now, what we're going to do is we're going to set the final energy equal to 0 because it's stationary. Basically, the end game is how far would this cart slide before coming to rest? Well, we've got negative a half mu squared equals ff times s. We already figured out what this value was. It was 350. That was the kinetic energy that it had. Now it's going to have none, so it's lost 350 joules. Negative 30 times s. And we get 11.7 meters. All right, so that thing would continue sliding for 11.7 meters. It would lose what little energy it had. All right, so imagine this bloke. He's accelerated the cart. He's done some useful work. He's expended 500 joules, but the cart only got 350. And then he watches it slide along, and now it's got 0. He goes, where did my 500 joules go? It's all just heat. All right? And that's where everything eventually goes. All of the energy that you will ever expend in your life is going to go to heat. Unless you make some weird monument with some bricks, and the bricks just happen to be stacked above the ground. So ignoring that, you walking around kicking footballs, and if you need, bunt, goal, yay, high five. All right, you're lying there in bed, you're giving off 100 joules per second just by existing. You're making heat. It's quite weird. Our cells need to be at 37 degrees because there's enzymes in our cells that will only work at 37 degrees. So we've evolved to lose energy. It's a very weird way to think about things. The very fact that we need to be at 37 degrees so that we function means that we are constantly losing energy. In order for us to function, we need to eat minimum 2,000 calories a day. And if we don't, then we fall over and die. All right? If we get too cold, our enzymes cease to work. If we get too hot, our enzymes cease to work. So we have to exist in this tiny little bracket between 36 and 38 degrees Celsius. Anywho, I'm sure it all has some purpose. What was I getting at? Oh yeah, all of the energy that you will ever do is inevitably just going to go to heat. The funny thing is, let's follow where that heat goes.
Everything doesn't matter. The funny thing is,
Let's follow where that heat goes. It goes into the environment, the atmosphere, it starts to warm up. So all right, now we've got this Earth and atmosphere that's slightly warmer. Well, we know from year 11 thermodynamics, it's going to radiate that out into space. Remember, the Earth is pumping out infrared, all right? So, and it's pumping out infrared at the same rate that it's getting it from the sun. All right, so we're in this little state of equilibrium where energy in equals energy out. You could then follow your energy. Eventually, all of your energy just radiates out into the universe in the form of infrared. All right, so wasted. It's not really doing anything useful. Okay, let's get to an equation. Yeah, let's say our skateboarder is initially stationary. This is quite fitting that Tony Hawk Skateboarder 1 and 2. Tony Hawk's Pro Skater 1 and 2 Remastered has just come out. Spent many hours playing that game as a child on PlayStation 1. No. There were, only had no multiplayer back then. The sum of energy initial equals... Let's add our initial mechanical energy. Let's add our initial thermal energy. In a lot of scenarios, we can ignore the thermal, all right? So you will often see, to make them easy questions, you will often see ignore the effects of friction or air resistance. As soon as you see that, then it's just a simple interplay between potential and kinetic. Now, we could write it out one further step. That's a half mu squared plus mgh initial. Well, conveniently for us, we've got no initial kinetic energy. So the total initial is simply because he is a 50 kilogram person in a gravitational field that is 4 meters above the ground. So we have a total initial of 1960 joules. Think of that as currency. That's how much you can spend. That's what you have to play with. And you can transfer it from one form to another. Okay? So, let's look down at point 2. I'll just circle point 2. I'll color code it. In green, we might want to go, what is his physical properties at point 2? How fast is he traveling? So we could then go, the sum of energy final equals the sum of energy initial, which is now going to equal a half mv squared final velocity plus mgh final. And we're going to ignore the thermal. And yeah, h final equals 0. So again, you can say, well, let's cancel that. Oh, and we can say now that it also equals 1960. I forgot the all-important energy. The total energy of this system is 1960. So then we can rearrange. We can say 1960 equals a half mv squared. I'm going to rearrange v now. I'm going to say that v equals the square root of 2 by 1960 divided by how much mass he had, which was 50 kilograms. Which was 8.85. Okay? Now, I'm going to just look at step 3. By the way, guys, I did miss something. It was in the video. You should be expected to rearrange your kinetic energy for M and for V. All right, so V is the square root of 2ek over M, or M is the square, no, M equals 2ek over V squared. So you need to be able to rearrange that without even giving it a second thought. I want to split scenario 3 into 2 scenarios. I want us to look at no friction, all right? In which case, at point 3, he's moving upwards. He's still on his skateboard, right? He has a little bit of potential, but the remaining energy, which sums to 1960, is in kinetic. He's slowing down as he rises back up. You're converting some of that potential, some of that kinetic to potential. But let's just go, what is V if there was no friction? What speed would he be traveling at? So let's just make this statement. The sum of energy final equals the sum of energy initial, which is 1960, which is now going to be a half mv squared plus mg h final. And we were going to set h final to 2.4. All right. So start throwing all the values in and we'll have one unknown. So 1960 equals a half of 50 v squared plus 50 by 9.8 by 2.4. Okay.
Convention?
No, not with energy because it's scalar. There's no direction. So let me just tidy this up. Would somebody mind telling me what his potential energy... Oh, no, it's 1176. So 1960 equals 25v squared plus 1176. And from this point, I'll need some help. Could somebody tell me what 1960 take 1176 is?
784.
784. Could you then please divide that by 25? Yeah? Anybody? 31.4. And then lastly, could you please take the square root of that?
28 on 5.
No.
43.7?
No.
28.
5 point...
Oh, that.
28.
Evaluate it numerically, please. Thank you. 5.6 meters per second. Now that should make sense because we've got a range of possible velocities. If he drops in, he starts off at 0. At the bottom, he's 8.85. So we know that the answer should be somewhere between 0 and 8.85. And it would make sense he's slowing down. So he's going from 8.85. At that point, he would be at 5.6 and getting slower and slower as he ascends back up to the top. All right. Could I now ask you to consider if this was friction? Let's just go at one last scenario. Let's consider this was maximum height.
Ooh. That's a doozy.
So let's suppose that friction acts, and as he goes up the half pipe, that's as high as he gets. So the question might be, how much energy was lost? All right. We make the same statement. All right. Hopefully I got the room here. With friction, we now have to bring in that new term. The sum of energy final equals sum of energy initial, which was 1960, equals K final plus EP final plus ET final. Apologies, I've gone off the page here. Hopefully you have some room. Let's rewrite it. 1960 equals half mv squared plus mgh final plus ET final. And luckily for us, you have to use a little bit of logic here, gentlemen. If that's as high as he gets, then at his maximum height, he is stationary. That's just a trick that you need for projectile motions, for motion up an incline, for motion up a half pipe. If that's his maximum height, then he has no kinetic energy at that point. Well, let's evaluate this. 1960 equals 50 by 9.8 by 2.4 plus ET final. 1960 equals 1176 plus ET final. The thermal energy lost is 784.
Yep.
Which, well, you might notice that number. If there was no friction, then that would have been the energy that he had in kinetic. Well, if he doesn't have kinetic at that height, it must have been lost.
How come that equals 25v squared? That's a coincidence.
Not a coincidence at all, because over here we said no friction, and here we said friction just stole that. You can't give it to kinetic energy. I've got it, and so that would have been the heat on the half pipe and the bearings of the wheel. All right. So friction creates heat when it is allowed to act over a distance. Okay. All right. Have a go of this one, please. I will add a few things. I want you to analyze this ball. We're throwing a ball upwards. We're giving it some initial kinetic energy. We're probably not going to have much time to do this. So maybe this is a homework item. I would like you to calculate one, maximum height. And then I'd like you to calculate...
He's throwing it straight upwards.
What do I want? Yeah, he's throwing it straight upwards. I want you to find maximum height. I want you to find energy on the, speed upon impact. And then, could somebody pick an arbitrary position between 1.5 and 13? 3 meters.
2.7.
You already said it. V at H equals 3. All right? So, that's going to be your homework task. For each of these questions, I want you to make that initial statement.
Are we assuming no friction?
Assuming no friction. Now, some of you might be a bit perplexed that we don't have a mass. And I will go through this as an example. You don't need a mass because it turns out that the m's will cancel. But if you're a little bit confused or worried, let's just say that he throws a 1 kilogram object upwards. So it leaves his hand with some potential energy and some kinetic energy. You need to find out what that is in order to solve part 1. All right? So it's going to have a half mv squared plus mgh. And I would like you to solve for those 3 different questions, please. All right, I better let you guys head off.
Yeah.
Don't we have 0 minutes left?
Yes.
No,
we don't.
We don't. 0 minutes. You got 5 minutes to get to your next period. I know you want to spend as much time doing physics as possible, but I've got to get to my year 10s.